Welcome back. In this video, we will examine the distance vector routing algorithm. As with the linked state routing algorithm, the goal of a distance vector algorithm is to find the least cost path between two nodes. However, distance vector algorithms use a different concept to come to a solution. The Bellman-Ford algorithm is a standard distance vector algorithm used on the internet. The algorithm is based upon the Bellman-Ford equation, which states that the shortest path, or lowest cost, is the minimum of the cost of a path from a source to a neighboring node, plus the cost from the neighbor to the destination, taken over all the neighbors of the source. Formally, we say that the least cost of the path from x to y is d sub x of y. This value is the minimum of c x to v plus d sub v of y, taken over all the neighbors of x. Let's see how this algorithm works. Look at this network diagram. We want the lowest cost path from node U to node Z. First, let's look at the directly connected neighbors of source node U, which are V, X, and W. The costs from U to each of these are 2, 1, and 5 respectively. To the costs from the source to each neighbor node, we add the costs of the path from those neighboring nodes to the destination. So we see that the lowest cost path through V goes through X and Y with a cost of 2 plus 5, or 7. The lowest cost path through W goes through Y at a cost of 8. The lowest cost path through X goes through Y at a cost of 4. This is the minimum cost of these three paths. So we select this path and put this information in the forwarding table. We found the shortest path in the last diagram by inspection. What makes this algorithm work in practice? From time to time, each node sends out its own distance vector estimate to directly attached neighboring routers. When a router receives a new distance vector estimate from its neighbor, it runs the Bellman-Ford algorithm to get the new distance vector estimate. Under minor changes, the DV estimate will converge to the actual least cost path. We will discuss what minor changes mean in a later slide. The DV algorithm is iterative and asynchronous and distributed among all the routers in the network. In the implementation of routing using the DV algorithm, each node exchanges DV messages with its directly connected neighbor. These could be initiated by an initialization, by a change in the cost of the local link, or a neighbor passing on a DV update from its own neighbor. The node then recomputes the path cost estimate. If the DV to any destination has changed, the node notifies its neighbors. If the DV has not changed, the node will not send the DV update. This next slide depicts a simple 3-node network. Using this diagram, we'll go through the algorithm's process. The leftmost group of the node tables shows the 3 initial forwarding tables for each of the 3 nodes. Within each specific routing table, each row is a distance vector. Specifically, each node's routing table includes its own distance vector and that of each of its neighbors. At initialization, each node knows the cost of the path to its neighbor, but it does not know what the neighboring nodes have for their DVs. In that case, infinity is used as the distance vector value. After initialization, the neighbors tell each other what their DV values are. From this, the Bellman-Ford algorithm updates the node tables with the new estimated minimum values. Let's look at the new table for node X in the center of the chart. Node X has accepted the distance vector costs from nodes Y and Z, but it has changed one of its dV costs. Nodes Y and Z say that their directly connected path has a cost of only 1. Now X, using the Bellman-Ford equation, compares the directly connected path costs to Y, which is 2, to the path to Y through Z, which is 7 plus 1, and determines that the direct path is still the minimum cost of 2. Node X makes no change to this dV value for Y in its forwarding table. Node X also compares the path costs to Z through Y, which is 2 plus 1, or the direct cost to Z, which is 7, and determines that the path through Y is the minimum cost of 3. Node X now changes this dV value for Z in its forwarding table. This next slide now shows the first iteration node tables for Y and Z. By using Bellman-Ford, as shown for node X, node Z has updated its path costs to X from 7 to 3, which uses the route through Y. The neighbors now send each other their new dV values. Bellman-Ford algorithm is run again, and no new minimum costs are found. The dV values are now finalized. This is shown in the grouping of the node tables on the right. Now, what happens when a change occurs to a network link? The node detects the change, recomputes its dV, and tells its neighboring nodes. In the example here, node Y discovers that the link cost to node X has been reduced from 4 to 1. We'll focus here only on the Y and Z's distance table to X. Node Y now runs the Bellman-Ford equation, which confirms that the direct path to X is still the best route to Y, with a reduced link cost. Then node Y also runs the Bellman-Ford equation for its path to Z, confirming that the lowest cost route to Z is still the direct connection. Now node Y sends its neighbor its new distance vector of 1, 0, 1. Node Z receives this information, updates its distance vector. This dV has the same path to X through Y, but a new cost of 2. Now node Z sends its new dV to its neighbors. This new dV is 2, 1, 0. Node Y receives node Z's update. Since Y's least costs do not change, the route calculations have converged. In dV algorithms, good news, that is, the reduction of route costs, travels fast. However, bad news travels slow with distance vector routing. Let's look at the simple 3-node network again. In the initial state, d sub y of x equals 4, d sub y of z equals 1, d sub z of y equals 1, and d sub z of x equals 5. Now the cost of the link between nodes x and y changes suddenly from 4 to 60. Node y now needs to update its view of the shortest path between itself and node x. It's no longer 4, but it's not 60 either. Since the nodes do not have a global view, y only knows that its direct cost to x is now 60, and that z last told y that it could get to x with a cost of 5. So by the Bellman-Ford equation, node y determines that the lowest cost path to x is still through z, but now has a cost of 5 plus 1 or 6. Then node y tells its neighbor z its new distance vector. At this point, node z needs to recompute its shortest path to node x. It knows it can get to y with a cost of 1, but it thinks still that y can get to x with a cost of 6. Therefore, this entry is no longer 5, but 6 plus 1 or 7. Now node z sends its new distance vector back to y. Node y then updates its distance vector for z. So y thinks it is now 8 units away from x and sends its new distance vector to z. Now z thinks that its shortest path to x is 1 plus 8 or 9. Node Z again updates its forwarding tables. This process repeats until node Z finally realizes that the shortest path to node X is the direct connection. After this counting up process exceeds the value of 50. This takes a total of 44 iterations. This problem is called the count to infinity problem, and the solution is called Poisson reverse. The idea here is that if Z has received Y's information that Z must route through Y to get to X, then Z tells Y that its distance to X is infinite. So instead of sending the distance vector 5, 1, 0, Z would send infinity, 1, 0. This would thus prevent node Z from routing back through Y, and immediately it would choose the lowest cost path to X, which is the direct path. Well, let's compare the linked state and distance vector algorithms. In linked state routing, each router knows the distance to its neighbor. Linked state information is flooded throughout the network to ensure all routers possess a synchronized copy of the area's linked state database. From this common database, each router constructs its own relative shortest path tree with itself as the root for all known routes. Distance vector routing is so named because it involves two factors: the distance, or metric of a destination, and the vector, or the direction it takes to get there. Each router knows the distance to its directly connected neighbor. Routing information is only exchanged between directly connected neighbors. This means a router knows from which neighbor a route was learned, but does not know where that neighbor learned that route. A router can't see beyond its own neighbors. If all nodes update their distances, the routing tables eventually converge. Now, linked state has a greater message complexity. With n nodes and e links, n times e messages must be sent. With very large networks, this overhead could be overwhelming. Distance vector has a smaller overhead because messages are exchanged between neighbors only. The linked state algorithm converges quickly. Transient route loops or oscillations may occur, but these are prevented by randomizing the times that each router sends out linked state advertisements. With distance vector, convergence time may vary. Routing loops are a concern. Poisson reverse can mitigate this problem, but not solve it in complex multipath networks. Well, how robust are these algorithms? With linked state, a node could advertise an incorrect link cost. However, the damage would be limited because each node computes only its own forwarding table. Flooding advertisement makes linked state extremely robust to failure. It is very unlikely that a node will miss so many advertisements that it has an incorrect view of the network. The DV algorithm is sometimes called routing by rumor. A distance vector node can advertise an incorrect path cost. Since each node's table is used by other nodes, errors can propagate through the network. In the next video, we will look at OSPF, a linked state protocol.